The Diels-Alder cycloaddition is just one example of a type of reactions called pericyclic. There are several different types of pericyclic reactions. We'll focus on the Diels-Alder, which was the earliest discovered and is widely used. All of these reactions share an important feature. They're what we call concerted reactions. All bond making and breaking occurs simultaneously. These are movements of pairs of electrons, two at a time, to make and break bonds, all happening at once. Quite different from the charge-driven reactions we've seen, and also quite different from the radical reactions, where we're talking about one electron movement. Take a look at this Diels-Alder reaction. There are two partners, a conjugated diene, simply known as the diene, and an alkene that has an electron withdrawing group attached. This is an electron-deficient alkene and is known as a dienophile because it likes dienes. This electron withdrawing group can be one of many things. Here are some examples. Any one of several carbonyl functional groups. The nitro group is common, and nitro is well known also. When the diene and dienophile are put together, often with heat but not necessarily, a cycloaddition happens. Those two partners form a six-membered ring, which we picture by occurring with a pair of pi electrons going to form a new carbon-carbon bond to the electron-deficient dienophile. But those electrons, while they're drawn there, can't form a bond unless this pair of electrons moves also, which forms a new carbon-carbon bond, but that can't happen unless this pair moves. So we have this cyclic movement of three pairs of electrons with the simultaneous formation of two new carbon-carbon bonds. Now I don't intend to get into it, but let me point out that if the diene had a substituent on it, for example here, this carbon could end up here, as you would guess, or that diene can flip around and that substituent could end up here. So there are two possible regioisomers that can form. Moreover, the dienophile can have stereochemistry, some substituent, and because this reaction is stereospecific, the electron withdrawing group and substituent shown on the same side of the alkene here will be on the same side of the ring here. Let me draw them this way. So there are both regioselective and stereospecific considerations to this reaction as well. This reaction is widely used to form six-membered rings. Having accomplished this reaction, you can do things with the double bond, you can do things with the electron withdrawing group, you can do things with the substituent here. So this provides a great versatility for making compounds that have six-membered rings. Now let me show you something interesting. You know, it was very easy for us to rationalize the formation of this ring by writing this cyclic movement of electrons, one pair here, one pair here, one pair here. And everything makes sense and it looks like, of course this makes a six-membered ring. Well, here's a case where you would think the same thing that doesn't happen. If this is an alkene rather than a diene, we have a dienophile on this side, we could picture the same type of cyclic movement of pairs of electrons to form a four-membered ring. Again, we'd have two new bonds. We need an explanation for why this top one works and this bottom one doesn't. Superficially, they look like both should work. Some very bright chemists had some insight about the molecular orbitals of pi systems that let us explain why this 4 + 2 cycloaddition works, but the 2 + 2 cycloaddition does not. Take a look. We're talking about a diene, so we know it has 4 pi molecular orbitals, 2 bonding, 2 antibonding. The 2 bonding orbitals hold all 4 pi electrons. And pi 2 is what we call the HOMO, the highest occupied molecular orbital. So this is the MO picture for the pi system for one of the reacting components in the Diels-Alder reaction. Let's look at the other one. This is an alkene which has 2 MOs, a bonding orbital and an antibonding molecular orbital. The 2 pi electrons, of course, are found in the bonding orbital. It turns out for understanding the 4 + 2 cycloaddition reaction of the Diels-Alder, we need to focus on the highest occupied molecular orbital of the diene. That's the partner from which electrons flow. And we need to focus on the lowest unoccupied molecular orbital of the dienophile. That's the partner into which electrons flow. So we're looking at the orbital that's highest occupied that has electrons, and the orbital that's lowest unoccupied that doesn't have electrons. Because we want to focus on these two, let's rewrite them, putting them next to each other. Below, I've written the physical picture. We have a diene and a dienophile, and we need to form a bond between the carbon atoms at the ends of this diene and dienophile. So we want to form this bond and this bond, which means we need to look at the molecular orbitals of the ends of the 2-pi systems. The ends of the bonding HOMO of the diene and the ends of the antibonding LUMO of the dienophile. And what was noticed by some very bright chemists is that when you line things up this way, the ends of these orbitals that are interacting have the same phase. Blue matches blue, yellow-green matches yellow-green. When these phases match, bonding can occur. If these phases don't match, bonding cannot occur. So for the 4+2 cycloaddition, the phases of the HOMO for the diene and the LUMO for the dienophile match, and the cycloaddition is what's called allowed. It occurs relatively readily. On the other hand, take a look at the same analysis for the 2+2 cycloaddition. Now we're talking about an alkene reacting with an alkene. So we have 2 MOs for one of the partners and 2 MOs for the other partner. In each case, there's a highest occupied molecular orbital. We'll look at the partner on the left, and a lowest unoccupied molecular orbital. Look at the partner on the right. When we try to match the ends of this pi system together with this one, the phases don't match. And for this reason, this reaction does not occur. In terms of this MO theory analysis, it's called forbidden. So while the 4+2 cycloaddition is allowed, the 2+2 cycloaddition is forbidden. So there you have it in a nutshell, the Diels-Alder cycloaddition. It's a 4+2 cycloaddition that has a diene partner and a dienophile partner. The structures of both can vary widely, so it's a very powerful tool for the synthesis of cyclohexenes.